So dear participants, with this particular lecture, we will continue our discussion on programmable logic controllers while we will be concentrating on counters. As we have already seen in the section of timers, that timers are not to be considered only as a part of PLC. There are dedicated timer modules that are available extensively as commercial facilities, and if you come across automated processes in industry, you will definitely find one or other timer that is installed into it. If that process is small and it requires only timing operation and some ancillary operations related to the timing that has to be automated, then there is no question of installing a PLC. Very good quality, reliable precision timers are available at very low cost that are to be installed in the system that takes care of the timing as well as timing related actuation or activation operations. With similar conceptual understanding in mind, you should look at the concept of counters. You see that counter modules are also extensively available commercially, and they are installed in every other system when you come across industry where some sort or any sort of counting application is there. Wherever you can see a counting application taking place, please do not come with the consideration or conception that there is a PLC. Dedicated timer units are available at different range of costs that can be applied for counting application. Such type of counters can be applied for up counting, that is the count will start from 0, and for each triggering event. Remember that every timer either increments by one count or decrements by one count with an external triggering event. This triggering event can come from sensor, definitely, but actually you need pulses. Digital pulse has to be applied to the triggering terminal. With each digital pulse, the counter increments by one count. So if it is an up counter, the counting starts from 0 and it will keep on counting till it reaches the preset value. Preset value means if it is a programmable timer. Now explicitly, whenever the timers are manufactured for industrial purposes, they are 100% programmable. That means you have to give a preset value of count. Whenever that particular count is reached, that counter stops counting, and at the output section, one or more than one number of relays, they are actuated. So once the relay is available at the output, you can make use of the NO or the NC contact as per your requirement. Remember that for small applications, if you require a counting application where there is a small process and purchasing a PLC for that small process is not financially viable or feasible or practicable, then you can definitely think of a dedicated counter unit that you can install there. So therefore, before going to the counters that are available with PLCs, let us have a generic concept on counters. You see, it can be considered as an electronic or electromechanical device, because you can see counters are also available in electromechanical format, where actually you will find dial sort of things, they get incremented mechanically. So either they can be electronic, completely electronic, or electromechanical device to count the events. Through proper means, you can see this second sentence, through proper means. That means that you have to apply triggering signal to the counter. Now, as I have told, this triggering signal is always in the form of digital pulse. So now you think you can just consider a conveyor belt through which some boxes are moving. You have to count the number of boxes that are passing through the conveyor. There you can easily think of a photoelectric sensor setup. You can think of a through beam sensor. Whenever a box passes, the beam of that sensor line is going to be interrupted. So whenever there is no box, you get full beam at the receptor, and whenever there is a box, the receptor or the receiver will be having no beam. So under one circumstances, under one condition, you will be getting a high signal, and when the box is there, you will be getting a low signal. So in this way, you can just translate the presence or absence of the box in terms of voltage level, high level and low level. That means you are able to generate pulse by the presence or the absence of the box. Now, if you apply these pulses to the input of the counter, then the counter will be either incremented. It's either increment its count by one count when the box passes, or it will decrement the count by one count when the box passes. So you can find here two more terminologies. One is increment and other is decrement. This shows that the timer can be of up count, that the counter can be of up counter type, or it can be of down counter type. In up counter, count starts from 0 and ends at the preset value. And in down counter, the count starts from the preset value, it ends at 0. However, in both the cases, if the count is completed, then there is facility at the counter to activate one or more than one relays. That already I have told you. Now you see that what are the counters in PLCs. If I talk very lucidly, then most of the PLCs are having down counting facility. But modern PLCs, they offer you up counting facility, down counting facility, as well as up and down counting facility. Since you are already conversant with the concept of timers, in case of counters, you will also find that there are some blocks. These blocks are nothing but IEC standard symbols, which are used to describe counters in ladder language. If there is an up counter, you can find the count in upward direction. If there is a down counter, you can find the counting in the downward direction. And in many PLCs, a very beautiful facility in the form of up and down counter combined in a single unit is available. I will take up one very easy example that might let you know that where this up and down counter in a combined unit will be very beneficial. I have also discussed about it at the end of this particular lecture. Suppose you have been given the responsibility of automating a parking lot. So definitely there will be a requirement to count the incoming number of vehicles and outgoing number of vehicles. And ultimately there will be a green light in front of the parking lot that will glow if there is capacity of taking more vehicles at the parking lot. That means if there is any vacancy for the vehicle, that green light will be on, and if there is no space in the parking lot, the green light will be off and the red light will be on, like that. So here you can find that when the vehicle comes inside that parking lot, count should be incremented by 1, and when some vehicle is getting out of the parking lot, the count should be decremented by 1. Now you cannot say for during the morning hours only vehicle will enter, during the evening hours only the vehicle will be exiting out of this parking lot, and accordingly you will be putting either up counter or down counter. This is not possible. At the same time, the up counting and down counting may take place. So under these circumstances, you can easily understand that what is the goodness of using an up and down counter. Now we will go further. This is the IEC symbol for counters, as we have found in timers. For counters also there are IEC symbols. You can see when it is CTD, that means it is a down counter, and when it is CTU, it is an up counter. There are several alphabetical things that you can find here. Since we have already crossed the topic of timers, we have known that whenever it is bool written like here, that indicates a boolean signal. Boolean signal means either it should be 0 or it should be 1. It will accept only these two format of data or signal. So you can see here the Q is the output, CD is the input that actually accepts the boolean pulse, that is either 0 or 1. This LD input in case of CTDs, and in case of CTU it is R. What boolean signal? Normally it is high, it will reset the counter. It will reset the counter, that means clear the counter to 0. Whenever some pulse is there at the CD input, the count will be incremented. Now in timer you have seen there is a preset function. Here the preset function is analogous to this PV, where you are putting an INT. INT means integer value. So here suppose you need to count up to 30. So in the PV terminal, here there will be definitely a window. Whenever you are in the ladder logic, you will find here a window in which you are to put the integer value. So you can put here 30. Once you have put here 30 and put your program in execution mode, then you will find that as the counts are going up or down, that value of count at that particular moment or at any particular moment is reflected across this CV. So this is the basic understanding of IEC symbols that you should have. Now you see, as we have seen in case of timers, different PLC manufacturers, they deal with counters in different manners. Now in some cases they are treated as relay coil and a rung output. As we have seen in Mitsubishi notations, you can find here, this is the thing I am talking about. This is the Mitsubishi generic notation. In this case, counters can be considered to consist of two basic elements that you need to remember. One is one relay coil to count input pulses. It will count the pulses, and one relay coil to reset the counter. The associated contacts of the counter being used in other rungs. As we have seen in our earlier discussion with timers, there is coil output at one rung and associated contacts in the other rung. The same will happen in case of counters also. You can find this is the Mitsubishi generic notation as we have already discussed. This is the reset input. This is the count input. Count input means the pulse input, and this is the actual counter contact that is associated with the counter. So you need one input for the reset, you need one input for the either up counting or down counting operation, and this is the contact which is associated with the coil of the counter, with the output coil of the counter. Now you see this is the Siemens typical notation where we can see that the counter has been denoted as an intermediate block. So now you can see the signals will be emanate or emitted from this Q output when the counting is over. These input pulses that are to be counted is given here in the CD terminal or CU terminal depending on whether the counter is a down counter or it is an up counter. Now you can see what is the basic counting circuit. In basic counting circuit we are talking of a Siemens typical notation here. We need actually two inputs. In the first input there should be an NO contact. When this NO is converted to NC, then the system will be reset and the count will be 0, and if the pulses are still present then it will start counting again. In the input 2 we actually apply the pulses so that the up count take place. Whatever I have discussed about, it is written here. It is written here that for 10 pulses we are going to go for this counting operation. When 10 pulse inputs, that is 10 transition from 0 to 1 have been received at input 2, the counter's contact will close and there will be a output from 1. If at any time during the counting there is an input to the input 1, the counter will be reset and it will start all over again. So remember that during the count, if you go for the reset operation, then you will have to again start from 0. The counter nature is not retentive. Now you can see this is how to program an up counter for Allen Bradley PLCs. We are talking of RS Logix notation, that is PLC 5, Micrologix 1000 family, 1400 family, 1500 family I am talking about. You can see this is the up counter block where this count up is written, which shows you that this is an up counter. The counter address is 5:1. 5.1 is the counter address. The preset in this particular case is 0 and 10, and initially the accumulator is at 0. Now in case of this counter there are not so much number of output as it was there in case of timers. So it is bit easy. Here you have got only two outputs. One is the count up output and other is the done output. You can see here that when the input pulses are being applied to the counter interface, then what is happening? The done output is remaining low for the entire period. And when this 10 counts are over, you can see over here 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. When this 10th count is there, then the down output is activated. And you can see this particular contact, the contact that you can see in the second rung, that is associated with the done output. So that will also be high since the done output is high. How the CU output will behave? The CU output will behave same as the input pulses. Once the input pulse goes high, the CU output will go high. When it is low, the CU output will go low. And you can also find that here is the operation of the accumulator. As each and every of the pulse is coming, the accumulator is incremented by one count. Definitely there will be a down counter, and in case of down counter there will be the opposite operation. However, remember, in any of the case, if there is a reset signal, then the accumulator will again come back to its initial value, that is 0, since it is an up counter. And in case of down counter also, it will be coming back to its original condition, that is 0, because definitely if the ultimate count at your accumulator is to be 0 only, because when it starts even a down counting, then you load it with some value that is there in the preset, the accumulator starts counting. The accumulator will start count like this 0 1 2 3 4, because it is taking place in the processor. But what you can see is, there you can see a down counting at your visual window.